This is Jack Jackson again, and in this video we're going to apply the Squeeze Theorem to help us work out a couple of limits. So this is in our little series of videos on some algebraic techniques and laws of limits that can be used to evaluate limits. So this can often be used, well, one place it can be used is where you see like a sine or cosine function, which we know is a bounded function. Sine and cosine are always between -1 and 1. And we can then multiply that by some other function, and oftentimes we can apply the Squeeze theorem. So sometimes that works. The first thing to notice is that e to the minus x is always a positive number. Never 0, never negative. And then the next thing to notice is that cosine of 3x, as I said, is between -1 and +1. So if I multiply a positive number by all three parts of this, the inequality stays the same way. So minus -1 times e to the minus x is negative e to the negative x. That's less than or equal to e to the negative x times the cosine of 3x. Which in turn is less than or equal to 1 times e to the minus x, which is e to the minus x. So notice we've manipulated this in such a way that we have our original function that we want to take the limit of in the middle, and we have it sandwiched between two other functions. In fact, we have it sandwiched between a function which is always negative on the left and a function that's always positive on the right. That part's not important. What's important is the fact that we have it sandwiched between two functions. Now, we can take, so that means the limit of the middle part has to be sandwiched between the limits of the two other parts. So, now when we apply this limit, this is where we apply the squeeze part. So we squeeze it. We squeeze this by taking a limit. Notice that the limit on the left, as x goes to infinity of minus e to the minus x, we know if we take a constant power to a larger absolute value but negative power, makes that whole thing go to 0. And this one, e to a larger and larger and larger power in absolute value but negative power, also makes that part go to 0. So in fact, both of these go to 0. Well, this thing that's in the middle, it just got squeezed in between 0 and 0, so that gives it no choice. Its limit must also be 0 by the Squeeze theorem. And of course we can see this in this picture. In the green graph is e to the minus x, which approaches 0 as we go further to the right. And the purple graph is minus e to the minus x, which is always negative here, but going up towards 0 as we go further and further right. And the original graph is the blue one here, and at least from this point on, it looks something like this. So it's up here, and it actually hits this graph. Actually, interestingly enough, doesn't hit it at the minimum. Maybe I can see it if I just zoom in right here. Yeah, you can kind of see it here. See, the minimum is happening just a little to the left at the spot over here where it actually touches the graph. Okay, but regardless, what's happening here is it actually hits these two graphs. It hits this one, then it hits this one up here, then it hits the one down the bottom, then the one at the top, crosses the x-axis in between each time. And so this thing is going up and down periodically like sine and cosine, but it's not really a periodic function, because a periodic function means you should be able to shift it to the right or left by the period and it stays the same, and that's not true here. But it does have some sort of regular behavior in the sense that it crosses the x-axis actually periodically. It has maxima and minima, which happen, at least as far as the x values happen, they happen periodically. But the thing is, it's going up and down forever. It never stops going up and down. If we looked way out here and zoomed way in, we would still see it going above and below the x-axis. But what we see is that amount going up and down is less and less and less and less and less. This is what we call damped oscillation. At some point here, all three functions are pretty much indistinguishable at this viewpoint from the x-axis, from y equals 0, So 0 is then the limit. Okay, let's try another one. Take the limit as x goes to 0 of x squared times cosine of 5x. See if you can do this one on your own and then come back and check your work here with the video here in just a second. Use a similar technique to the last problem. Press pause now. Okay, well, similarly to the last problem, we notice that the x squared is a positive number, greater than or equal to 0, positive or 0, and the cosine of anything is between -1 and 1, at least where it's defined. In fact, this function is actually not defined at 0. Cosine is defined just fine, but 5 over x is not defined when x is 0. So that's where it kind of messes up. So at x equals 0, this thing is undefined, but it might still have a limit there. So there could be a hole in the graph. Let's check this out. Well, everywhere this is defined, at least, we know that the cosine of 5 over x is between -1 and 1. X squared is greater than or equal to 0, no matter what. So multiply by this positive, or non-negative at least, number x squared by all three parts, and we get negative x squared is less than or equal to x squared times cosine of 5x, which is less than or equal to x squared. So we have sandwiched in between the minus x squared and the x squared our original function. So our original function is like the peanut butter sandwiched between these two pieces of bread. And now we're going to run over it with a steamroller. We're going to squeeze it. So we apply the squeeze theorem. This minus x squared, take that limit, and the limit here. The limits have to be in the same order if these functions, if these are always in the same order, at least for all x's except for 0. The one in the middle is undefined at x equals 0. So we don't let x be 0, we let x approach 0, and we notice that these two limits on the right and left here both go to 0, so that leaves nowhere for the one in the middle to go but 0. So in fact its limit does exist, and that limit is 0 by the squeeze theorem. And we can see that in the picture here. X squared, y equals x squared is the green graph. You know what that looks like. You've seen that one a lot. Y equals minus x squared is just that graph upside down. So these both actually include the point at the origin. And then the function we have is jumping up and down between those two. So as we go further out to the right or left, it doesn't have a limit. It keeps getting widely oscillating, getting bigger and bigger oscillations as we go to the far right and far left. So if we were to take the limit as x goes to infinity of this function, it would just not have a limit. Same way for minus infinity. As x goes to minus infinity, this has no limit. And it's not even infinity or minus infinity because it's actually approaching sort of both and everything in between. As you go up this way, as you go further out, this thing gets arbitrarily large, but it also gets arbitrarily way down in the negatives as well, and takes on every value in between as it's going up and down, higher and higher. But look what happens here as you get in closer and closer to the origin, closer and closer to x equals 0. Whoops. There we go. You can see sort of a close-up here, and what's happening is this is going up and down and up and down. And actually, it actually goes up and down infinitely many times as you get in here close by. So it's a little bit hard to actually draw it at all. You can't really draw what's happening right here. It's actually continuous everywhere except at 0, but it's going up and down infinitely many times, say between -1 and 1. It crosses the x-axis infinitely many times. Pretty wild function there, isn't it? But at x equals 0, it's undefined, but it is approaching 0. And that's what we just proved using the squeeze theorem. So the squeeze theorem, it can sometimes be used, and this is kind of how you might go about doing it.